All right, so we're going to be looking at integrated rate laws, chapter 12, chemical kinetics. We're going to be looking at problem number 41. And number 41 gives us a reaction. In this reaction, we see NO2 plus CO2 yields NO and CO2. And then what we have here is we have a table in the center. This, on the left side, you see time measured in seconds. On the right side, right here, you see molarity. And this is all for NO2. So then the problem is asking us to determine the rate law, the integrated rate law, and the value, we'll mark this down here, the value of the rate constant. Additionally, it's looking for us to solve for NO2 at 2.7 times 10 to the 4 seconds after the start of the reaction. All right, so the way you want to look at this problem initially is that you have a table. So when you have a table, you have to first determine what type of rate is this. Is this going to be 0, second, third? What type of order of the reaction is this going to be? So in order to do that, what we need to do is we need to create a graph, and we need to make sure that one of these values produces a linear type of relationship. So let's do two things. Let's assume that this is going to be a first order reaction. So on the left side here, what I did is I wrote down, assuming that it's first order. So what we're going to do in order to solve to see and figure out if it is a first order, you're going to take the natural log of the concentration. Now, the reason why you're going to do that is due to the fact that whenever you see a first order reaction, you take the natural log of the concentration, and in doing so, you should be able to produce a straight line. In a first order reaction, concentration will affect the rate directly. If it does, N will equal 1, and then the expression is expressed as rate equals K times concentration to the power of 1. All right, so let's figure this out. So what I did is I took the natural log, and then I took the concentration. So if you have your calculator right now, take natural log of the first value that I have here on my table times 0.500. And we have three numbers, 3 sig figs. I get a value of negative 0.693. Okay, and I do this for these consequent numbers. I'll take the natural log of 0.444, 0.381, etc. And then I get these values. Okay, thereafter, I want to be able to create a graph and graph this over time to see if I get a straight line. But before I do that, I need to make sure that it's going to be either first order or second order. So what I did is I grabbed the values for the second order. And for second order, we see here that the concentration changes the rate to the power of 2. So N will equal 2. Thus, our expression is going to be rate equals K times concentration all raised to the power of 2. If this is true, then we will produce a straight line in our graph, and then it'll be second order. Okay? So it's either going to be first or second. So let's take this 1 over concentration. And that's exactly what I did right here. Assuming our second order, we're going to take 1 over our concentration. We're going to grab our concentration from the table, 1 over 0.500. So put that in the calculator right now. And I get 2. Now remember that there are 3 sig figs, so it's going to be 2.00. And I do the same for the following values, and then I get all of these values. Now, we make a Cartesian coordinate system in which these values here are going to be in our y-axis, and time is going to be in our x-axis. So when you want to look at these values, look at the values so you can have in your head how you're going to scale these graphs. So I see right here that on my second order, my highest number is 5.75. So what I did right here is set my highest number to be 6 and my lowest number to be 0. And this is going to be all in my y-axis. So this will be assuming second order, 1 over NO2. And on my other side here is going to be assuming first order. So assuming first order, this is going to be natural log over NO2. And I'm scaling it by looking at these numbers. Negative 1.7 is my my lowest value here. So then I put negative 2.0 and my other value, which is 0. Okay, so I got my y values set up. Now all that I got to do is set my points and graph and figure out which one's going to give me that linear relationship. And I went ahead and graphed these already. I put these correspondent points, like these points, I put them in blue, as you can see here. Okay. And what I want you to notice is the type of line that we're getting in this reaction is we're getting kind of like a small slope at the bottom. So it doesn't produce necessarily a straight line. So now let's look at our second order reaction. This is our second order. And by plotting these points versus the time that we got from our table up here, and this is the time down here in our x-axis, and this is time in seconds over 1,000. So I scaled the time in the same way. You know, we looked at 0 and our highest is 1.8 times 10 to the 4. So I went ahead and put it at 18. All right, so then when I plotted my second order assumption values, I get more of a linear type of relationship. Okay, so then this means, oops, let's get a different color here. All right, so this means that indeed we can assume it is a second order reaction. So this gets a check mark, second order. Now we can go ahead and continue to solve the problem. So the plot of 1 over NO2 versus time is a linear type of relationship that we're looking for. Thus, the rate law and the integrated rate law are going to be as follows. Rate equals K is our constant times NO2, all raised to the second power, as we saw in this graph. All right. Now, the integrated rate law will be as follows. 1 over NO2 will equal K is our constant, time, plus 1 over NO2 naught. So the problem did ask us to determine the rate law, the integrated rate law. Okay, we've done those two. Now we'll need to solve for the value of the rate constant. In order to solve for the value of rate constant, we have to look at the slope, because remember, we have a linear type of relationship. So what we'll do is we will then solve for our slope. Our slope is going to give us our K constant, which is delta y over delta x. And where do we get these points? We're going to get them from our table. We're going to get these low point, high point from our y-axis. So then it'll be 5.75 minus 2.0 over our x-axis, which is going to be our time, and we're going to get that from the table that they gave us, 1.8 times 10 to the 4th minus 0. 1.8 1.8 times 10 to the fourth minus 0. Now remember, this is all in seconds, and this is going to be in molarity minus 1. If you put that into the calculator, we should get 2.08 times 10 to the negative 4 because of our significant figures. Our units are going to be in liters over moles times seconds. All right, so this is our constant. So we're going to square it and save it for later for the second part. Now we have to determine NO2. Now for the second part of the problem, they're telling us we solved this part, we solved this part, we solved the value of the rate constant. Rate constant's going to be our K. Now what they want us to do is to calculate concentration of NO2 at 2.7 times 10 to the 4th second after the start of the reaction. So what we'll do is we're going to take 2.7 times 10 to the 4th, and this is going to be in seconds. We're going to use the integrated rate law that we used earlier, right here, 1.1 over concentration. Okay, 1 over NO2. This section right here, not. And we're going to get our values from the table. First value, 0.50. So 1 over 0.500 molarity. Put that into the calculator, we get 2.0 molar minus 1 for our units. All right, so I'm going to square that as well. Might come in handy. So let's continue. Then it'll be then 1 over NO2 then equals KT plus 1 over NO2 naught. So let's go ahead and get these values and plug them in. This is our K, all right? 2.08 times 10 to the negative 4. This is the value that we just solved. This is our K. And this is in liters over moles times seconds. And all I'm doing is I'm multiplying it, as you see right here. What is the time that they gave us to solve? This is the time. Times 2.7 times 10 to the 4th. Okay, and this is all over seconds. Plus 1 over NO2 naught. We already solved 1 over NO2 naught, and it's right here. So it's going to be plus 2.0 minus 1. Now, if we put all of this into the calculator, we should be able to get, second here, should get 7 point, we got 3 sig figs, 7.62. And now we're almost done. 1 second, 1 over 7.62. We're almost done. See, because our final answer is in our integrated rate law tells us that it's a second order reaction. We have to put 1 over NO2. In this case, we solved for NO2. This is our value for NO2. So now all that we have to do is put 1 over 7.62, which should yield 0.131233. So 3 sig figs, so it's 0.131. And that is the answer.